Okay, so let's talk about the three types of acceleration. We have two types of displacement, velocity and acceleration. We have linear and rotational. However, this picture is not quite complete. We learned about a third type of acceleration earlier. Can you remember what that was? Centripetal. That's right, center seeking. This was covered earlier in the uniform circular motion chapter, and you can go back there to review it if you like. This is the acceleration that a point on a rotating disk feels that keeps it moving to the center of the circle. So remember, that acceleration is v squared over r. The v in the above equation is the v we've been working with, which is the tangential velocity of an object located on a rotating disk, or a rotating object. Up until now, though, we've just called this the linear velocity, but we're going to need its tangential nature to discuss acceleration. Okay, so look at this disk below here. It shows linear acceleration that we've defined, as well as the center-seeking acceleration. But centripetal acceleration is also linear. So we will rename the linear acceleration we've been dealing with in this chapter and call it tangential acceleration, because it's tangent to the surface or tangent to the circular path. The angular acceleration alpha is a vector that points out of the page. Don't worry about that now. Vectors pointing out of the page will be covered in electricity and magnetism, and also in the APC mechanics course. So that would be when you go off to college and you take calc-based physics. I did cover the k-hat direction in the 518 course as well, and I will do that again when we talk about magnetostatics. We now have three accelerations associated with a rigid rotating body. We have tangential, which is tangent to the circular path. We have angular, and we have centripetal, which is the center-seeking acceleration. And they all are related to one another. Can we express all three of these accelerations in terms of the angular velocity of the rotating object? Let's go ahead and give it a try with these equations. So here we have the tangential acceleration is r alpha. The centripetal acceleration is v squared over r. And we know that the tangential velocity is equal to r omega. So go ahead and see if you can relate all of these to alpha. Okay, if you need more time, go ahead and pause the video. So let's take a look. We know that the tangential acceleration is r alpha. That's defined. And we know that that's equal to r delta omega over delta t. We know that omega is equal to v over r. Okay? And that means that we can replace this v squared in the centripetal acceleration equation. We can substitute in r omega for v. And then we end up with r squared omega squared over r. Well, r squared over r just gives us r. So the centripetal or center-seeking acceleration is just going to be r omega squared. Okay, so now we've expressed the tangential acceleration in terms of omega, and we've expressed the centripetal or center-seeking acceleration in terms of omega. Well, we know alpha is defined as delta omega over delta t. And so there you go. You can go ahead and see that we, here we have alpha from this definition, right? So we've put that in, and we can see that we have related these to the angular speed or angular velocity. At which point is the magnitude of the center-seeking acceleration the greatest? Go ahead and pause if you need to. Okay, so let's see what you chose. The correct answer is A. A is where you have the greatest center-seeking acceleration, right there. Can anyone tell me why? Think about the definition of center-seeking acceleration, and that will give you your answer. Okay, so let's talk about total linear acceleration. There are two types of linear acceleration. There's tangential and there's centripetal. Notice that they're perpendicular to one another. So what do we have to do when we have two perpendicular vectors? How do we add them together? That's right, we're going to use Pythagorean theorem. So we know that the total acceleration, the total linear acceleration, is going to be the square root of the tangential acceleration squared plus the center-seeking acceleration squared. A student pushes with a constant force a merry-go-round with a radius of 2.5 meters from rest to an angular velocity of 3.0 radians per second in 8.0 seconds. What is the merry-go-round's tangential acceleration? Go ahead and pause now. Okay, so let's see if you calculated the correct answer. You should have gotten 0.94 meters per second squared. If you didn't get that, go ahead and send me a note through Edmodo. For the previous problem, what is the merry-go-round's centripetal acceleration at 8.0 seconds? Go ahead and pause the video now. Okay, so let's see if you calculated the correct answer. You should have gotten 23 meters per second squared. Again, if you didn't get the correct answer, go ahead and send me a note in Edmodo. What is the merry-go-round's total linear acceleration for the previous problem at t equals 8.0 seconds? Go ahead and pause the video now. Okay, you should have gotten 23 meters per second squared. A bear pushes, with a constant force, a circular rock with a radius of 7.2 meters from rest for 5.0 seconds. If the center-seeking acceleration of the rock at t equals 5.0 seconds is 4.0 meters per second squared, what is the angular velocity? Go ahead and pause the video now. Okay, so let's see if you calculated the correct answer. You should have gotten 0.75 meters per second. Again, if you didn't get these right, please go ahead and send me a note in Edmodo. What is the rock's tangential acceleration at t equals 5.0 seconds? Pause the video now. Okay, you should have gotten 1.07 meters per second squared. What is the rock's total linear acceleration at t equals 5.0 seconds? Pause the video now. You should have gotten 4.1 meters per second squared. Okay, in the next video, I'm going to talk about angular velocity and frequency.